All right. Good morning, everyone. Thanks for joining us for today's webinar. We're excited to unveil Farsoon's latest advancement in the polymer additive manufacturing, the HT601P-4, designed for large format, high throughput production with quad fiber laser. I'm Alex, and I'm your host today. Joining me are three experienced speakers from the Farsoon team. First, we have Ray Jones, our application and technical pre-sale. Next, we have Matt Amin, Senior Service and Application Engineer. And finally, we have Johnny Zhu, our Polymer Production Line Manager. In today's session, we'll be covering the following topics: a brief introduction to Farsoon technologies, and then we'll dive into key features and capabilities of HT601P-4. And then we'll have some real-world applications, and we'll close with a live Q&A session. So feel free to drop your questions in chat anytime. Let's dive in. Ray, over to you.
Thank you, Alex, for the introduction. And I want to thank everybody for joining us today. Before we get into the meat of the presentation, I want to introduce Farsoon as a company, who we are, what we offer. So Farsoon Technologies is a global leader in industrial additive manufacturing, specializing in laser powder bed fusion technology, both on the polymer side and the metal side. With over 25 years of experience, Farsoon has grown into one of the most recognized names in the field. We have an impressive global footprint operating in 30 plus countries, supported by a robust network of resellers and offices. What truly powers our innovation is our team, with 700 plus global experts working across R&D, manufacturing, support, and management. And the result of our global team speaks for itself, with over 1,200 Farsoon systems being installed worldwide. Our key regional offices highlighted on the map include Austin, Texas, which is the home of Farsoon Americas, Stuttgart, Germany, which serves as our European hub, and then, of course, our global headquarters is located in Changsha, China. Each of these locations plays a critical role in driving Farsoon's mission of making industrial AM more open, accessible, and powerful for our partners around the globe. So what does Farsoon offer? At Farsoon, we not only offer machines, we provide a full spectrum additive manufacturing ecosystem tailored to meet industrial demands. Starting with our machine solutions, we offer a truly open AM platform with a broad and flexible machine portfolio. Our systems are designed to deliver high quality parts and machine performance while remaining among the most cost efficient options on the market. We also offer customized solutions for unique customer needs. On the material side, we support a wide range of PA12 and PA6 based materials, including reinforced options. Farsoon invests heavily in material R&D, manufacturing, and we work closely with third-party partners to expand options and material performance. Our software solutions are equally robust. We provide tools for build preparation, machine operation, real-time monitoring, and we offer an open architecture that empowers users with flexibility and control. When it comes to applications, we take a customer-centric approach, offering process engineering, benchmark production, and full testing and qualification support to ensure success across all industries. Finally, what really sets us apart is our commitment to a fully open system, meaning full access to materials, parameters, and collaborations. This openness gives users unmatched freedom to innovate and scale. So introduce Farsoon Americas. We're proud to have a strong presence in the US through our Farsoon Americas branch headquartered in Austin, Texas. We offer a dedicated local service team to ensure responsive and expert support, and an established local inventory with key components sourced directly in the US, reducing lead times and ensuring operational efficiency. And professional customizable training delivered on-site at the customer's location, tailored to each user's needs. Our experienced US team includes specialists in sales, technical support, and applications engineering. And we're all committed to supporting our customers every step of the way, whether it's pre-sale consultation, machine servicing, or advanced application support. So getting to the meat of this presentation, right? So our new machine, our Flight 601P quad laser system. System is designed for manufacturers who need high throughput without stepping up to say the 1001, which is a larger platform machine. With our four 300-watt fiber lasers and high chamber temperatures, the 601P supports demanding high performance polymers while maintaining incredible speed and build quality. And it's really what we're seeing now. It's a game changer for industries, especially aerospace, automotive, and the energy fields that demand both volume and performance. So productivity and ease of operation. Let's take a look at some core strengths that make the Flight 601 quad laser an ideal solution for modern and high demand production environments. So first we have the large build platform. Offers a 600 by 600 by 600 build chamber, millimeter build chamber. That's a total volume of 216 liters, perfect for either producing large single parts or efficiently nesting smaller components in one job. This significantly increases part output per build cycle and helps reduce the cost per part, making it ideal for industries that rely on volume, especially automotive, aerospace, and industrial tooling. Second, we have ultimate throughput, right? So equipped with those four 300-watt fiber lasers, the system delivers an exceptional sintering speed without sacrificing quality. Each laser works in parallel to drastically cut down build times. And because the 601 uses an exchangeable powder cartridge system, you can prep for the next build while the current build is running. That means minimized downtime and nearly continuous production, which is a real game changer for manufacturers focused on efficiency and economy of scale. Next, we have compact machine design. So despite its power, it has a very compact footprint of just 3.5 square meters, which is just a tad bigger than our 403 systems, if you're familiar with those. This is critical for facilities where floor space is at a premium. Additionally, a system is designed for complete front side operation, making installation flexible and operator access much more efficient, especially in multi-machine setups for automated production lines. Next, we have high temp capabilities. So the max chamber temperature is 220 degrees Celsius and has an advanced multi-zone thermal control system that we'll get into a little bit later. And it supports a wide variety of engineering grade polymers. This includes materials like PA6, PBT, and even TPU on the lower end of the processing temp side, which are essential for demanding applications in sectors such as electronics, aerospace, automotive. Access to these materials opens the door for high performance parts that must endure temperature, wear, or even chemical stress. Next, we have consistent part quality. So achieving quality at scale requires consistency, right? This is where the 601 really shines. Using advanced scanning strategies and a highly efficient powder delivery system that ensures every layer is uniform. Adding in real-time surface temperature monitoring and the optional infrared camera, you can really get detailed live insight into the build process. And this helps catch anomalies early and ensures that part repeatability across multiple builds. Next, we have ease of operation. So the 601 is built with the user in mind. It's user-friendly software, and interface makes it simple for operators to control, to monitor, adjust builds in real time. The design enhances both flexibility and efficiency, allowing the end user to focus on production and less time on troubleshooting. Together, these features, from throughput to thermal control to software and layout, make the 601 a truly well-rounded solution for advanced high-end polymer additive manufacturing. So kind of looking at the footprint of our 403, our 601, and our 1001. As you can see, the 601 delivers a compelling balance of both build size and machine footprint. It offers a 612-liter capacity, which is nearly 2.5 times more than our 403, with only a slightly larger footprint. This makes it ideal for users who want to scale production without a major increase in facility requirements. Compared to the 1001 quad laser system, which offers 225 liters, but it demands almost twice or more than twice the floor space. The 601 sits kind of in that true sweet spot, large enough for industrial scale batches, yet compact enough for space conscious manufacturing environments. So kind of taking a look at some key tech data for the 601. As we can see, the build envelope, 600 by 600 by 600 millimeters, four 300-watt fiber lasers working in tandem and dynamic focusing. The system achieves a high-speed sintering with fine detail, which isn't really readily available in other machines currently on the market. But it's not just about speed and power, right? It's about control as well. The multi-zone heating and the real-time temperature monitoring really ensures thermal stability throughout the build, which is something, if anybody is familiar with SLS knows that temperature is the key ingredient to successful builds. Uh, and the ability to process advanced materials, right? Like carbon fiber, glass fiber, polymers, and then of course our in-house developed BuildStar, MakeStar software. Users can really adjust build and part parameters on the fly and monitor every layer of the build to ensure that they're getting the best build out of every machine. So looking at a couple compatible materials for the Flight 601, the system is optimized for over 20 types of printable polymer powders, ranging from standard nylons to high performance engineering grade materials. So let's start with the PA11 and PA12 materials. These materials offer excellent mechanical strength, chemical resistance, and durability, ideal for functional parts and automotive or industrial applications. Farsoon's materials like our 31 or 3401 glass bead material, our 3201, these are available in black and an off-white color. These options give users both performance and aesthetic flexibility. Moving on to PA6 compatibility, the 601's process chamber, again, is 220 degrees Celsius. So we're able to produce or process these higher end engineer grade materials. Like PA6, our glass filled PA6 and our carbon fiber filled PA6. These are key applications where high stiffness, thermal resistance, or weight reduction are priorities for the end user. And then we also have partnered with some other material manufacturers that have produced materials like PPS, PBT, and a couple other specialty type materials. This flexibility is critical for advanced manufacturing sectors, especially aerospace, medical, and energy. So talking about CO2 and the fiber lasers, the key difference is laser beam spot size. So traditional CO2 SLS systems use a laser with a spot size between 400 and 500 microns. This usually restricts our minimum feature size to about 1.5 millimeters, or about twice the size of the laser spot size. We can see though with the fiber laser, we can get down to around 100 microns in the contour or outline paths to get a real fine feature detail around 0.3 millimeters. But we're also able to open up that fill pass to 100 or 1,000 microns rather to decrease build times. The second key difference is laser power. So the standard operating range for CO2 lasers is between 30 and 120 watts. Fiber lasers, which are traditionally used in metal laser powder bed fusion systems because of their more dynamic powder range, can access wattages between 300 and 500 watts. This gives us not only an overhead on material processing ability, as some materials may need more laser energy than others, but also unlocks a significant increase in scan speed from 10 meters a second on the low end to 20 meters a second, which we find in our flight systems. And then the last key difference between CO2 and fiber lasers is their average lifespan and operational stability. So on average, a CO2 laser has a lifespan of approximately 40,000 hours, which is between 4 and 5 years of operational use. The power stability of the laser, how much it drifts during operation, can reach upwards of plus or minus 6% during extended continuous usage. On the other hand, a fiber laser, because of its unique construction, has an average lifespan of 100,000 hours, or about 10 years. So this significantly increases the value of the machine and reduces maintenance and replacement costs of multiple CO2 lasers over that same uh, period of time. So looking at the scanning strategies of the 601, so we're looking at impressive speed increases and part quality, and that lies in the laser coordination strategy, how the 4 fiber lasers interact and divide the build area. So you can see how the machine scanning field is divided. Lasers 1 and 2 each have full access of the left side of the build chamber, while lasers 3 and 4 cover the right side. And then there is a central overlapping zone that uses lasers 2 and 3. Uh, so we have two different modes that we can utilize during the build process itself. So the first one we have is speed mode on the left side, bottom left side of the screen. In speed mode, the scanning algorithm prioritizes productivity. So larger parts or groups of parts can be divided among multiple lasers to maximize scanning speed. Each laser works concurrently, dramatically reducing the build time while maintaining excellent part quality. In advanced mode, which is on the bottom right-hand side, this focus shifts to dimensional accuracy and surface consistency. Each part, especially in the overlapping zones, is assigned to a single laser to avoid any deviations that could occur if more than one laser is used at the same time. This is especially useful when building highly detailed or precision critical components. Together, these two scanning modes give operators the flexibility to choose between maximum throughput or maximum precision based on the in-use application. It's another example of how the 601 adapts to production needs, whether you're building batches of industrial parts or intricate in-use components. So looking at production efficiency, you can really see what really matters at the end of the day, right? How many parts can you produce per build, and how efficiently your system turns powder into parts. So this comparison highlights the output from various systems using an industry standard 10% packing density as kind of the baseline. So the Flight 601 is capable of printing 200 parts per build, significantly more than the 80 from both the Flight HT403 dual laser system and more traditional CO2 SLS systems, and far beyond the 37 parts that would be built in a MJF system. This is largely due to the taller build height of the 601, 568 millimeters of vertical space. So you're able to take full advantage of not only the larger 600 by 600 of the X and Y, but also Z, enabled to vertically nest those parts together. What's even more impressive is that the 601 produces those 200 parts in just 15 hours and 40 minutes. Compare that to the Flight 403 dual laser, which takes about 12 hours to produce 80 parts and 37 parts in 11 and a half hours using MJF. This result is faster build cycles, shorter downtime, and higher daily output. So looking at our optimized thermal management for the 601 system. So the thermal control is one of the most critical factors in selective laser sintering, and it's an area where the Flight 601 really excels. So let's walk through the thermal management features that ensure consistent, high-quality parts every time. So the first thing we have is real-time monitoring of the thermal field. So we offer a optional infrared thermal imager or camera. This allows operators to track temperature distribution across the builds in real time, identifying anomalies early and adjusting as needed, a key tool for preventing warping and improving overall yield. Second, we have piston heating. The piston or the build plate ensures precise heating with a maximum temperature variation of only plus or minus 5 degrees Celsius across the surface. This consistent heat distribution reduces thermal gradients, which are a common cause of internal stress and warping in those in-use printed parts. Third, we have multi-zone independent temperature control. So this system uses 10 independent heaters, each capable of being controlled separately. This multi-zone architecture allows the chamber to maintain a stable, even thermal environment, regardless of part geometry or build density. Fourth, we have our optical system cooling. So despite the high temperatures in the build chamber, the 601 protects its opticals using a central water cooling system. This ensures that the laser optics remain isolated from thermal fluctuation of the radiant heat from the build chamber, maintaining a stable temperature of around 32 degrees Celsius throughout the builds. This means better accuracy and longer component life of those lasers and galvos. Fifth and final, we have our cartridge heating. So cartridge rolls are heat controlled, which helps in maintaining consistent temperature on those outer edges and through the Z height of the build. This highly engineered thermal system is what really allows the 601 to handle engineering grade polymers like PA6 at a high throughput without sacrificing quality. And it gives users a perfect balance between productivity and precision. So kind of building on the previous thermal management slide, I wanted to highlight just how precise and effective the 601's heating system really is. So the first thing we have is our advanced IR heating layout. The 601 uses a highly engineered layout of infrared heating tubes to distribute heat evenly throughout the build area. What you're seeing on the left-hand side is the internal arrangement of these heating elements, paired with the optional IR camera that tracks thermal behavior using every layer of the builds. And then on the right-hand side, let's see if I can get this video to play. We have a real thermal image video or picture. Thank you, Alex. So this is a video or a thermal image video of a build being captured real time during the print cycle. So this shows the uniform temperature distribution, less than plus or minus 3 degrees Celsius variance across 95% of the build area. That kind of consistency is critical for ensuring uniform shrinkage, minimal warping, and an excellent layer-to-laser sintering. What does it mean for production? This level of temperature stability ensures full field uniformity, high consistency, and stable surface quality, and gives us a more predictable production process, which is key for scaling and manufacturing. So let's take a look at our advanced control card for the optical system. This plays a big role in part quality. This is used mainly for managing the laser path in the 601. So higher compatibility, first, the control system is designed with broad capability in mind. It supports a range of laser path configurations, making it suitable for current and future generations of scanning hardware. Key benefit for future-proofing production setups. The smart scanning with uniform energy input. It uses a smart scanning algorithm to maintain consistent laser speed and energy density across the scan path. That means whether the laser is drawing a straight line, a curve, or a corner, the material gets the same energy, no hot spots, no undercentered zones. Self-developed precision algorithms. This consistency is made possible by Farsoon's own proprietary control algorithms, which are specifically designed for additive manufacturing. They allow a fine-tuned real-time control of how the laser behaves as it navigates complex geometries. If you look at the images below, we can see the difference this makes, right? So on the left-hand side, you have an example of inconsistent energy at sharp angles, resulting in deformation or uneven sintering. On the right, you can see the improved output, crisp, clean lines, even at sharp corners and right angles. This is the kind of detail and accuracy that matters, especially in applications where precision is a requirement, like medical, aerospace, or even fine mechanical parts. This advanced control system is part of what gives the 601 its edge, not just in speed or power, but in laser accuracy, feature clarity, and surface quality uh, finish. And then one of the most important trends in additive manufacturing right now is the integration of real-time monitoring and vision-based process control. And the Flight 601 features both of these built-in infrastructure for visual inspection and data logging. So we have an industrial camera inspection module, which we can see in the upper left-hand corner. The system includes a dedicated space for a industrial camera module designed to oversee the build area during the print. This allows for future expansion of vision-based features that's ready to evolve with the end user's operation. This also adds a layer of visual quality control, especially for detecting early powder or recoding anomalies, warping, FOD within the builds. And then we have print process monitoring and recording. So the camera system continuously monitors the powder recoding condition and laser scanning status throughout the print. So this gives operators live insight into the process and allows for better documentation, informed troubleshooting, and then post-build analysis for process optimization. So looking ahead, this platform is already being designed to support defect detection. This includes using visual algorithms to automatically detect powder defects and layer inconsistencies during the build. These features will help identify issues before they compromise a part, further improving yield and reducing waste. So while the 601 already supports robust process monitoring today, it's also designed to grow into a fully automated inspection system, providing users with a future-proof path towards lights-out production. Now I'll hand it over to Matt, who'll go over manual operation of the machine and its components and a few real-world applications using the Flight 601.
All right, thank you, Ray. That was excellent. Everybody hears me okay? One of the ways that the 601 achieves a exceptional balance of productivity and efficient use of space is an innovative material handling system. If you're familiar with the 403 and the 1001 systems, you may see that the material handling system of the 601 is an innovative hybrid of the best of both systems. It has a top feed, bottom supply method, meaning that there's a large hopper similar to the type used in the 1001 that feeds into a supply hopper above the printer, which then drops powder down into supply pistons similar to the 403 that provide powder for recoding the platform. This approach, it gives a continuous supply, which means that you have no worries about having enough powder for a full build. And you have the precision of the bottom feed method for recoding. So I'll go into the next slide, which goes into that in a bit more detail. All right, you can see on the right in the diagram, I'll take you through step by step how this works. Number one there is the powder supply bin. So that's a 225 liter supply bin, which is enough powder for a full 216 liter build. So not only is it enough for a full build, but it has the flexibility of being refillable in process. If, say, you're not doing full-size builds, you're just doing continuous smaller builds, you have the flexibility for operators to refill while it's in process. So that gives operator flexibility for continuous manufacturing. So that supply is pumped up to the top feed bin, which provides powder to a dosing bin, which is similar to the mechanism of the 1001. That bin then gravity drops a dose of powder down into number 4, which was the unique design approach that the 601 takes. That is what's called a movable powder delivery cartridge. And that cartridge will translate forward to refill the bottom feed bin, which you see there's number 5. So that bottom feed bin is somewhat analogous to the feed supply bin that you'd have on a 403. And what this approach does, it allows that bottom feed bin to be continuously refilled as the build progresses. And the recoating method is very similar to the 1001, is that you have a roller that moves from back to front, and it's supported on both sides, so it's very stable and robust. And there is a return bin at the front, which again is similar to the approach that the 1001 takes. So you have a method that is very compact and yet supplies continuous supply in a precise recoating method. And another real advantage of the system is that it very effectively isolates the powder resupply from the chamber, both by having the movable powder delivery cartridge being a box which contains powder, and there's also, if you can see in the video, there is a curtain. So this very effectively seals the chamber and the platform from intrusion of any loose floating powder. So your chamber remains cleaner, the recoater remains cleaner, which assists with precision. The other advantage is this method really reduces the amount of powder overflow, excess powder going in. Effectively, the overflow is limited to any kind of residual leakage coming down from the dosing bin at the back of the chamber. So it doesn't require either a large overflow bins or a recirculating system like the 1001. So it's a really innovative approach, and it enables that compact footprint yet high throughput that is the hallmark of this printer. So go to the next slide. Oops. Okay. So the other great feature of the 601 is the way that its design is optimized to continue production workflow. What Farsoon refers to as CAMS, the continuous additive manufacturing system. As you can see at the top, the little animation, that this system is front loading and front removal of the cartridge. So again, that is helps achieve the compact floor space and ease of operation. Another innovative approach is you can see that the build cartridge for the 601, it does not have the wall heaters incorporated in the cartridge. The wall heaters are in the printer. So this allows for the build cartridge to be simpler and lighter. And also by having the heaters in the printer, you have a very consistent heat for any cartridge. You don't have, it eliminates the possibility of a heat variation between build cartridges. So that helps get the consistency from build to build that production operation is going to require. So the transfer cart, you can see, is similar to the transfer cart for the 1001 system. It has rollers and the crank for moving the cartridge in and out of the machine, and then it can be transferred. What you see above to the right is the breakout station. So that cart can be moved over and transferred into. So those transfer carts are quite maneuverable, fairly compact, which allows for flexibility in the use of space and how the customer wants to arrange a space efficiently for operations. So the diagram you see across the bottom, again, it just shows the flow. You have a continuous powder supply to the top of the machine. The cartridge removed to breakout, and then for customers who do have industrial throughput, the PMS, the powder management system, is an option. So for refilling those cartridges with the powder mix that you select for your operations and efficiently move. And this diagram shows how a hypothetical customer could set up a CAMS operation using 601s. You can see with the front loading method that you can build a fairly compact but high volume method with machines facing each other to have a central aisle for adding and removing cartridges, moving them to a cooling area, and then a breakout area, and then powdering and seeding. So in a pretty compact floor space, you can achieve an efficient flow and high volume production. So one thing, we don't have a slide showing that there is a cooling cap, nitrogen-based cooling cap for the build cartridges. It has an insulation wrap around the cartridge and connections for nitrogen. So you can achieve a measured cool down of your builds to maintain part quality and consistency. So just an example of an application here. In this case, material, the FS3200 PAF, the P11 like, it's a PA12 material that's been engineered to have PA11 like performance. This is a great example. You can see where 601 will shine is a very large part that can be produced quickly with high accuracy and quality. So this type of a automotive application, you can see that's a very complex part. We've got a lot of radii and complex internal structure. So the solution, you see structural integrity and integration through combining all that complexity into a single build. And high volume, again, with 4 fiber lasers, you can achieve a part production like that in quite rapid time, and obviously rapid iteration and reduce cost. And next, the other option is a very large volume of small to medium parts. In this case, we can see an example of the 6140 GF nylon 6 PA6 material. Again, with the precision thermal control and precision scanning with a material like PA6, you can still achieve a very high precision. And with the precise heat control, minimize your heat distortion. So excellent for that type of material at either large size or high volume, where in, say, in electronics applications, you need, in particular, high accuracy for part-to-part fit. So that, oops, this was the last slide. I guess we did. Okay, that completes our presentation. I want to thank everybody, Ray in particular, for doing such a great job at the start, and we can open to questions and proceed from there. Thank you to everybody.